Good day, students. Today we are going to discuss the second experiment for BTech Electrical Protection 4. Myself, Dr. Krishnamurthy, lecturer for the Electrical Protection course at CPUT Belleville campus. In the first video clip, we discussed about the first experiment, that is the fault analysis and time overcurrent protection setting using SCL751 relay model. I think in my first video clip we discussed briefly from the scratch how to model the power system network in the Digsilent environment, and also we spoke about the settings for the relay models, and we also discussed the different characteristics of the overcurrent relay, that is your inverse and definite and the combination of both the IDMT. So from the first video clip we are having strong fundamental knowledge on the protection setting and implementation and verifications of the protection setting in the Digsilent environment. In the second video clip, we are going to discuss the time overcurrent protection coordination and grading settings and verification using the Alstom KCGG142 overcurrent relay model. That is part of your second experiment. So let's scroll down to the exercise manual. Okay, the aim of this experiment to implement the time overcurrent protection coordination for this 5-bus network that is given in figure 2 using Alstom KCG142 relay model. The first step in this project, as described, we need to implement this 5-bus power system network in the Digsilent environment. That is, you need to model the network from the scratch, and the second part, we also make sure the power system data for this single line diagram must be according to the data that is given in the manual. But as I told you in the first video clip, the students are familiarized how to model the power system network in the Digsilent environment. So to save our time, I am not going to start from the scratch. I assume you can follow the first video clip in order to familiarize yourself how to model the network in the Digsilent environment. So in this video clip, I just want to emphasize the protection settings and also the coordination between the relays. Okay, we can speak a little bit about what we are going to do in this exercise. As we see in the single line diagram, the grid is supplying a power to the network, and there are 4 overhead lines. It's a short transmission lines which is having just 10 kilometers and 11 kV lines. The lines are the same length, and the ratings and specification of all the 4 lines are the same in this experiment. And in the downstream we have a customer that is connected on the 11 kV which is feeding from bus 5. So what we are trying to achieve from this experiment, we need to make sure to understand the protection coordination and grading between the relays. That is the main objective of our exercise. So for that simplicity, I just used the Alstom overcurrent relay, which is placed on every bus from bus 1 to bus 4, and bus 4 is a downstream which is directly connected to the load, so we are not using a relay on bus 5. So as we seen from the diagram, our aim is to include the CTs and the relay which is configured to the circuit breaker which is connected to bus 1. The same thing you need to do for bus 2. You have another CT, second CT and the relay 2 which is modeled to control the breaker on bus 2. The same scenarios for bus 3 and bus 4. Okay. Next, move on to this case. I assume you can use this power system data and model the power system network from the scratch. Next, we discuss about the instrument transformer settings. So as we seen in the single line diagram, we have 4 CTs which is located on bus 1 to bus 4 respectively. So the CT details are given in table 2.5. So you can see the protection device name, that is relay 1 to 4, which is connected in location bus 1 to 4 respectively and is connected to the branch line 1 to 4 respectively, and all the relays are the same type, that is this is basically an overcurrent relay from Alstom. That relay model is KCGG142 1 amps relay. And if you look the CT slot, we have a CT1 for the relay 1, and for the phase element and from the ground element the CT ratio is 100:1 amps. It means the primary side is 100 amps and the secondary side is 1 amps. Okay, so all the CT ratios for all the 4 CTs for the phase and the ground elements are the same. Next, we also want to discuss a bit about the overcurrent setting. It is very important in order to understand the coordination between the relays and the grading margin that we are going to apply. Okay, when you look at, there are 4 relays as we discussed. So we start from table 2.6, will give the overcurrent relay settings for this 5-bus network. So you can see relay 1, there are 2 stages, stage 1 and stage 2. I think if you see this greater than symbol 1, it means stage 1, and double greater than symbol 2, it means it's referred to stage 2. So the stage 1, let us assume the current can be given in primary side or secondary side or in per units, but for discussion purpose I emphasize on the primary currents. So the stage 1, the primary current is 100 amps and the time setting is 0.25 seconds, and the characteristics we just selected as normal standard inverse IEC. Okay, and for the element 2, you see the element 2 is 1015 amps and the timestamp, the higher the current, the timestamp we getting 0.38 because it is a definite characteristics. And the same thing applies for relay 2, for relay 2 stage 1 and stage 2, but you can see the primary currents will be 100 amps for stage 1. This will be the same for all the 4 relays, but stage 2, if you look, it is 576. It means from 100 to 1015 you will getting a IEC curve, inverse curve, and from 1015 onwards you will get the definite curve. But in this case for relay 2, 100 to 576 you getting the inverse curve, from 576 amperes onwards you will get the definite curve. And you also note there is a significant reduction in the values of the fault current values or maybe the current setting values compared to stage 2 of relay 1 and stage 2 of relay 2, because this we assume it is a radial feeder network. It means the fault current values is more in terms of close to the source side. Let me show from the single line diagram. The fault current, if you introduce a fault here, there will be a more fault current on the source side compared to the fourth end. For example, if you apply a fault here, the fault current will be minimum because the fault current, according to the location of the fault current gradually moves or decreases towards from the source. I guess you understand the principles of how the fault current varies with respect to the location from the upstream to the downstream of the network. So in relay 3, the same thing you need to follow, but make sure you see the stage 1 is 100 is keeping as the same like relay 1 and relay 2, but stage 2 of relay 2 is 400 amperes. You can see in relay 2 is 576 and relay 3 is 400. As we spoke, the fault current will decreases which you move away from the source. And relay 4, you see again 307 amps in stage 2 compared to 400 amps in stage 2 in relay 3. Okay, now we are happy about the setting that we are going to apply for the relays from 1 to 4. I can see from the source to customers downstream of the network. And also you need to take note the time dial settings. In this case, for stage 1 we making 0.25 seconds. For stage 2 is a definite characteristics. So what we making for all the stage 2 elements will be a same time setting. That is, if you look 0.38, it means from 0.38 is a definite characteristics. The time will not change, will be constant. So you can see from 0.38 will be the same time factor for element 2 of relays 1 to 4 respectively. But while you compare the timestamp for inverse characteristics, relay 1 is 0.25 seconds, but relay 2 you can see there is a significant reduction, that is 0.20 and 0.13 and 0.08 respectively. It means the timestamp is decreases from relay 1 to relay 4 for stage 1. That is for the standard inverse. Okay, now we also want to discuss about the relay coordination, the principles of the relay coordination. Before we discuss, I will show you what outcome we are looking from this exercise. Okay, first step, we need to model the 5-bus network that is given in figure 2.1 in the Digsilent environment as we seen in the video clip. Then once you model and you need to conduct the load flow successfully, I assume from first video clip you know how to model the network and conduct the load flow. Once that is done, next we need to include the overcurrent relays on buses 1 to 4. In this case you can see there is a I can zoom and show you quickly. In this picture the video clip you can see the relays. So we can also apply a color shaping for your single line diagram. So you can see the relays will be defined in green colors. So that's why in all the cubicles you can see from bus 1, 2, 3, 4 they are in green. It means the relay models are there. Okay, but I will teach you how to include the relay models on those cubicles. So once we have the relay models, and we need to make the settings for the CTs and the relay models. But this exercise will showing the outcome how it's going to be look. But anyway, we can delete the relay models and we can model again. And once you're done, we need to plot the time overcurrent plot, something similar like this. In the time overcurrent plot, you can see the relay 1. You see the colors of the relays in the time overcurrent plot. Relay 1 is in red color. So this is the inverse characteristics of relay 1, that is your stage 1, and stage 2 must be your definite characteristics. And according to the settings, we need to make sure the current setting values and the time setting value for your relay 1. Quickly look at that scenario. What we see here, we can see your relay 1, that is 100 to 1015. So it means from 100 amperes to 1015 amperes we are expecting an inverse curve. From 1015 onwards we expect the definite characteristics. So as we go quickly here, I think this is your 100 amperes. So this relay is starting from 100 amperes to 1015. Okay, so this is approximately 1015. We expect an inverse characteristics. From 1015 onwards it's going to be a definite characteristics, and the definite characteristics, the timestamp also we applied 0.38. It means this is 0.1, 2, 3 and 38 is close to 4. So that's why we getting the definite characteristics as it is. Okay. And let me look for the relay 2 setting. Relay 2 setting, what we looking here? We looking 100 to 500 and 656. It means 100 amps to 500 and the relay 2 is in green color. Okay, if you look here for 100 amperes to 516, is it 516? Sorry, 576. So this is your 500. Okay, so 576. So you can assume from here to here. I think this 100, 200, 300, 400. This is 500. Okay. So this is close to 600. That's why we getting 576. This line is 600, but little bit before this line. So you assume from here to here is 576. From 576 onwards is going to get a definite characteristics. And relay 3, you can see for relay 3 100 to 400 amperes. So it means we expecting relay 3 is blue in color. From 100 to 400 you get a inverse characteristics. From 400 ampere onwards you are going to get a definite characteristics. And the last relay 100 to 307. So it means from 100 to 307 amperes we will get a inverse characteristics, and from 307 amperes onwards we will get the definite characteristics. Okay, so that's the characteristics curve. We are looking something similar like this, but we will see. We need to model and we apply the grading, then we can draw the time overcurrent plots and we can get the stage. But now I am directly showing the outcome what you are looking for, better understanding the theoretical principles of the relay coordination. Because of that settings that we discussed, the settings for relay 1 to relay 4, that's why there is no overlapping of the characteristics curve. There will be a minimum coordination between these relays, 4 relays, and also there will be a grading can be applied between these relays, so that we can verify the protection setting of this case. Okay, let's continue. So from that principle, what we are trying to understand the relay coordination. It means we have more than one relays. In exercise 1 only we have one relay, so there is no possibility of coordination can be achieved. So to understand the coordination, that's why we include more than one relay. In this case we have 4 relays, and our aim is to how we going to coordinate these 4 relays. Okay, come back to that point. In theoretically it explained in the manual what is relay coordination. For your understanding, I quickly review that part. The principle of relay coordination is explained with the help of the figure 1, which we shows already. We have a series of radial lines and the time distance characteristics associated with the inverse time relays. What we are trying to say, the relay operating curve selected. How we select the relay operating curve? That is this curve. The relay operating curves are selected for each of these relays, plotted as a function of the fault location. So it means wherever you apply the fault is going to be plotted against the fault location. Since we understand the magnitude of the fault current decreases as the fault moves away from the source. So what do you mean? The magnitude of the fault current decreases. It means if you apply a fault here which is far away from the source, the fault current will decreases. If you apply a fault here at bus 1, the fault current is more compared to the fault current which you applied a fault on bus 5. So that's why the principle is saying the fault current decreases as we move away the location of the fault from the source. Source is this your external grid. Okay, I guess you understand the principle. Okay, now we need to understand the coordination principle. For that simplicity, with the help of the single line diagram, we assume there is a fault F1 which is the farthest from the generating source. It means you can see the fault is at the end of this network, that is at bus 5, which is far away from the source. Your source is at bus 1. Okay, then in that case what will happen? If fault is F1, relay R4, that is the relay which is close to your bus 4, and this CB must be operate first. Okay, let me discuss that point. If there is a fault on this bus, relay R4 must operate and the breaker at bus 4 must open for these fault conditions. Okay, but this relay R3 will also see the fault, but it will not trip this breaker, because the timestamp, that is the time dial setting of this relay, will be faster compared to the time dial setting of the second relay. Are you getting that point? For it means if the fault is here, this relay will see the fault and this relay also see the fault current value, but this relay will trip first before this relay will trip. Why? Because the time dial setting of this relay is faster compared to the time settings of this relay. Okay, let me go to the point again. For fault F1 at the farthest from the generating source, relay R4 C-bit breaker operate first, relay R3 at breaker as a higher timestamp level, which includes a coordinating time delay to the breaker 4 if it can. The same thing will happen. Relay 2 also have this relay also will see the fault, because if the fault is here, relay 4, 3, 2, 1, everybody can see the fault, but only this relay will trip because the timestamp of this relay is fastest compared the time setting. This is smaller compared to the time setting of this relay. For any specific reasons, let us say the breaker failure or anything happened to this breaker, then it fails to trip within the timestamp setting, then this relay will trip for the next highest timestamp. Okay, and the same thing after this timestamp, this is the next timestamp relay, so after this one this will trip, and after this one this will trip. Okay, so that is the principle that we applied for coordination time. That's why if you go through this coordination time, you can see the first relay will operate in 0.25 seconds. So after some timestamp, you can see the second relay which is going to operate in 0.20 seconds. Okay, after 5 minutes delay, 5 seconds delay, and after some time delay from 0.20, like say 0.07 timestamp delay, this relay 3 is going to operate in 0.13 seconds. But this is a time dial setting, but the actual tripping time will include the context times of the relay, so we see the actual time in the time overcurrent plot characteristics curve. Okay, so that is the principle they explained here. Okay, I hope you can read the theoretical aspect and to understand the things. So, and also in part of this exercise, I would like to also emphasize to verify the relay coordinations and its tripping time. In this exercise, we applied a 3-phase unbalanced event, because this is unbalanced network, so we need to use to conduct an unbalanced load flow and also an unbalanced fault for the different location of the power system, and verifies the fault magnitude and the relay tripping time as given in 2.7. I quickly go through the table 2.7. What we doing into what the data is given in 2.7. We applied a fault, that is unbalanced fault on bus 5. Okay, and the fault current value is monitored. The fault current value you getting like 301 amps, 0.49 amps, and the relay, that is because bus 5 is close to the load, so the relay R4 will tripping at 0.47 seconds, and then your next relay will tripping at the next higher timestamp. You can see 0.78 seconds, and the next relay will tripping the next higher timestamp 1.2 seconds, and the next relay R1 will tripping at 1.57 seconds. So it means if the fault is bus 1, bus 5, first relay R4 will trip, and after some time delay, that is the grading, your R3 will trip. After the grading, some grading margin, your R2 will trip, and if you add the grading margin further, your R1 will trip. Okay, then the same thing we applied the bus fault at bus 4. In this case, you can see when you move the fault close to the source side, the fault current is increasing. You see, when you move towards the close source side, the fault current is increasing from 301 to 388, and you can see for bus 4, relay 4 will not see the fault, but relay 3 will see the fault. That is, the tripping time is 0.4 seconds, and R2 is 1.02 seconds, and R1 is 1.27 seconds. For your understanding, I can also show the scenarios in the Digsilent environment. For instance, you can say the fault is applied on bus 4. Okay, the fault is applied on bus 4. Let me align the network quickly. Okay, this is bus 5. We can apply a short circuit, but it is an unbalanced circuit, is right. So when we apply unbalanced short circuit, we can see the fault current value, which is 301 amperes, and also we need to monitor the tripping time of the relay. So it means because there is no relay here, so you can see there is no current flows through, and the timestamp is close to 100,000. Is 100,000? Okay, 100,000. So it means the relay is not tripping. But if you come to this place, the fault currents remain the same, because this is a one is going from up to source. But you can also monitor the tripping time, but you can see the tripping time is 0.4 seconds. For this case, tripping time is 0.78 seconds, and this one is higher than the previous one, 1.2 seconds, and this one is 1.5 seconds, 1.57 seconds, but the fault currents remain the same. This is the one that is describing in this case. Okay, for case 2, they are saying about we apply bus fault, 3-phase unbalanced fault at bus 4, and we need to verify the fault current value and also the tripping time, and we make sure the relay 4 is not tripping when the fault is at bus 4, but all other relays will trip, but the timestamps will be taken into note. Let's quickly do that. This is bus 4. We can apply a fault short circuit. Okay, if you compare the fault current magnitude, you can see this is 388 according to the data that is given in the table. I think this table 2.7, but you can see for this fault, okay, this relay is not tripping because your relay is, the relay is sitting after the bus, so the relay will not see the fault at all. This relay will not see the fault at all. That's why this relay is not tripping. But if you compare this relay will see the fault, so it is tripping at 0.64 seconds, and this relay is also see the fault. It is tripping higher timestamp compared to the previous one, 1.0 second, and this relay will be higher timestamp 1.27 seconds. So it means if the fault is here, these all 3 relays will trip. But the time origin, we can say there will be an increase in time origin, which will move towards the source side. Okay, so that's why we're proving relay 4 is not tripping, but all other relays are tripping. The same scenarios we apply for bus 3, bus 2 and bus 1. Quickly show you that things as well. If you apply bus 3, you can make sure the relay at bus 3 is not tripping, R3 is not tripping, but your R2 and R1 is tripping, and also your R4 is not tripping. R4 and R3 is not tripping. Your R2 and R1 is tripping with higher timestamp that is given here. So you can see your R3 and R4 is not tripping, and these 2 relays are tripping. The last case we need to apply, and also the fault current, you can see from this side the fault is here, so the fault current from this to the source must be a 0, but from up to here the fault current we getting about 544 amperes. From here to here there is a fault current there. Okay, the rest of the scenarios as the same. You can apply bus 2 and bus 1 and verify the fault current and the tripping times, the relay tripping times according to the table that is given in 2.7. So from the table what we understand, it is understood that the relay farthest from the power source has minimum fault current value. So we need to making a grading between the relays in order to be 0.3 seconds. But in the Digsilent I will explain you later how to apply the grading. But in this exercise the grading is chosen 0.3 seconds is the grading between the relays. Okay, but we will speak more in detail about how to apply that grading. So this section will speaking about how to apply the grading. Okay, as part of the exercise, they also describe what we need to do. So before we come to this description, okay, we make sure we go to the models here. Okay, so what you want to do now, I think we assume you already build up the network. Once you build up the network, you need to conduct the load flow. Make sure this is unbalanced network, so the load flow that you are conducting must be unbalanced. If you use a balanced load flow, it won't execute, it give you some type of error message. Okay, because it's unbalanced, execute these things. Okay, are we happy about that first stage? The second thing, okay, we need to conduct the load flow before modeling the relay models, and after we conducting the load flow, you need to validate the load flow results as we explained in the first video clip. You can select a different option. You can look the bus terminal results, or grid summary, or total summary, or the complete system report. You can execute, and you can go to the maximize command window, and you can validate the load flow results. So you can see the load flow is computed Newton-Raphson algorithm, and it is converged within 3 iterations. The load flow was successful, and we can also able to see the bus voltages and the voltage profile, and we also happy with the voltage profile, which is plus or minus within plus or minus 10%, and we also able to see from the results your complete voltage profile for the 11 kV, and also we can see what is the load and the external in-feed to the network, and also we can get the total summary of the results with giving the total power flow of the network that you consider. So that is the first step, but I am not explaining how to model the network from the scratch in this video clip, but I assume from the previous video clip you know how to model the network in the Digsilent environment. But if you are not familiarized, I strongly advise or recommend to watch the first video clip again and to familiarize yourself how to model the network in the Digsilent environment, and to familiarize yourself to how to conduct the load flow and verify the results of the load flow from the first video clip. Okay, now back to the business for this exercise. Straightly, we need to include the overcurrent relays. So what you need, you select the first cubicles, okay, and we go to new devices and select a relay model, and you go to the relay and select a new project, and from the project, sorry, it's not a new project, cancel this one, go to select a project type. From the project type, you need to select your KCGG142 amps relay, but this is under your relay library folder. But before doing that, you also make sure that you already imported the relay model Alstom KCG in your relay library. It means you go to your relay library. I think we did in the first video clip, but I assume you also imported the relay by following the first video clip. So it means you can see from the GE Alstom this relay model, that is your KCG, but using inside KCG there are different overcurrent and earth elements, but for this exercise we are using this one, KCG142 1 amps relay. But if you didn't import, first you need to deactivate the project and import the relay from the relay library, which is available in the Word drive. Otherwise, this KCG142 relay, the relay model also available in the Blackboard. You can download the relay model and import it, and you can watch the first video clip, the procedure how to import the relay model to your network. Okay, so we need to select the relay model. So once we select the relay model, I'm not going to do it because I assume already in my case I have the relay models. So if you go here, what I can do, I just edit the devices. If I edit, you can see I have the relay model KCG142 on the specific location, and also I have the CTs here. But you know the procedure to include the CTs also. You can right click the cubicle and bus 1 and go to new devices and select a current transformer. From the current transformer, you go and create a new current transformer, and you specify your primary is 100 amps and your secondary is 1 amps. Okay, this is 100 amps and this is going to be 1 amps, and you can apply, and then you can also name the CTs, that is CT1 because it is sitting on that side. The same procedure, then we can click OK. But in my case I already have the relay model, so I don't want to repeat the steps to include again the devices. So in my case I want to see the devices, so instead of new devices I'm going edit devices. So I need to make sure there is a relay and there is also a CT. Quickly review the CT. If you look here, this is a CT which having 100 amps on the primary and 1 amps on the secondary side, and the phase technology is 3 phases and the rotation is ABC. If I go to this one, it's a different tap rating, but I'm selecting this 10 to, these primary taps are 10 to 500, but I'm going to select the tap which is for 100 to 1 amperes because you selected the taps here. If you go down here you can see all the taps, but our selected taps is 100 amps. Okay, cancel. And for the relay model, you make sure after you include the relay model, our aim is to import the settings as specified in the manual. So first we need to check your phase CT. There's 100 and to 1 amps, star connection, ABC and 3 phase rotation. We happy. The second one is also the same, but this is for 3I0. Okay, that is for the phase and the earth fault condition, earth elements to monitor. Okay, you see 3P and 3I0. And we also want to make sure stage 1 and stage 2 for relay 1. For stage 1, if you look, the stage 1 must be standard inverse. You select from the standard inverse. In the first exercise also we used the standard inverse, but you used IEC, but that comes with the specific relay model 751, but this is Alstom relay model, so there is no IEC. They are saying about DT standard inverse. Okay, definite time standard inverse characteristics curve. And also we make sure the current setting is 1 amperes and the time dial setting is 0.25 seconds. To verify this, I refer the manual again. We can refer the manual table 2.6. So you can see the stage 1, we are entering the secondary current, so 1 amperes and the time setting is 0.25. So this, and the standard is, the curve characteristics is standard inverse. So you make sure these 3 things: standard inverse, 1 ampere secondary current and 0.25 seconds for stage 1. Okay, for stage 1. And for stage 2, again you look the manual. We need to make sure that this is tripping direction is none. We are not going to apply for stage 2, but we make sure the pickup current 10.15. You can refer the manual 10.15 the secondary current, and the time dial setting is 0.38 seconds. This is stage 2. You see the 2 primes are that stage 2. And you see your stage 3. If your stage 3 is active, make sure you make out of service stage 3, because for this exercise we only covering stage 1 and stage 2. Stage 3 is not in service, so you make sure it is out of service. As I told you in the previous video clip, if the specific element is out of service means you can see there is a hyphen. If the specific element will be in service means there is a tick mark. So you make sure you only able to the tick mark for the selected elements, that is stage 1 and stage 2. All other elements which are not focusing for this exercise must be in out of service. So this is I0 stage 0 and I0 stage 2 and I0 stage 3 must be out of service. And the last thing, your trip logic. But we don't worry about the trip logic, as we showed, it already configured to the specific cubicle. So you don't need to make the setting. It can find out the nearest cubicle with the breaker which is going to be when the relay issue a trip signal, which switch must be operator for this case. Okay, for instance, if I click here, it's already configured, so it means the cubicle 1, the relay 1, the switch is there. It means the bus which having bus 1, the switch is there, that switch will be there. But I will show you in the single line diagram again. Sorry. And logical 2/3, I think this is must be out of service, so you make sure this is out of service. Okay, that's it. Again I review the setting for this relay 1. sorry, we need to make sure your stage 1, okay, as per the data given in the manual, and stage 2, that's the two important things, and CT1 for the phase element and the ground elements, okay, and all other elements must be out of service. Trip logic will automatically configure. That's the only thing you need to do for relay 1. Okay, we are happy about that. Next, you need to include and relay 2 on bus 2. For that, you need to select the breaker which is close to the bus 2, that is this breaker. You right click and go to new devices and add your relay model, and select, you go to the relay model, select the project and add KCGG142, but in this case I already have it, I'm not going to do it, I skip these steps. And also you need to also include new devices and add your current transformer as well. So go here and select from the project, you can select the current transformer, otherwise you can also select a new project and you specify 100 into 1 amps your primary and secondary. Okay, I guess you are familiarized with those steps. Now we need to make sure, for in my case I have the CTs and the relay model, so I'm going to show the settings for this relay 2. So I just directly go to the edit devices, so I can directly go to my CT. My CT, again I tell you, I'm showing you 100 amps is 1 amps. All the CTs in this exercise, we have 4 CTs and all the 4 CTs have the same ratio, 100 is to 1 amps. Okay, you can also refer that things in the relay manual in table 2.5. You can see all the tap changings for relay 1 to 4 is 100 into 1 amps. Okay, next we go for the relay setting. Again we make sure the CT2, the name is CT2, 100 is to 1 amps, and also your CT2 is also phase element and ground elements 100 is to 1 amps. And the next important thing, stage 1. For stage 1 we need to make sure that is 1 amperes and 0.2 seconds. So if you go to your manual here, for relay 2, this is 1 ampere secondary and 0.2 seconds. And for stage 2, 5.76 and 0.38. Okay, we are happy about the stage 1 for relay 2. This is stage 1, prime 1 you can see. And stage 2, 5.76, 0.38. Okay, the time dial. Current is 5.76 per unit in secondary and 0.38 seconds. And this is stage 2, you can see prime 2 there. Okay, we are happy about that. And logic, as I told you, it configured automatically, but make sure that logic 2 over 3 is out of service, and also make sure the elements which you are not using, for instance this I0, stage 1, stage 2, stage 3, everything must be out of service. Okay, we are happy about that. Next we need to include relay 3 on bus 3, this cubicle. So I'm not going to repeat the step. You go to right click and new devices and add the relay model and configure to all stump KCG142 relay. Next, after you done, you go to new devices and add the current transformers and edit the datas. Okay, now I'm going to directly show you edit devices. We can see the relay 3 settings because I already include the relays. Let's see the settings for this. You have CT3, that we have 100 is to 1 amps for phase element, and for the ground elements also the same. Next we have to look for stage 1. For stage 1 is a standard inverse. This is stage 1 for relay 3, and we make sure the time dial setting is 0.125 seconds and the current setting is 1 amps secondary. So go to relay 3, you see relay 3 is 1 amperes and the time dial setting is 0.13 seconds. Okay, this is something 0.125, so we are in the right place. Okay, it must be 0.13 seconds, so let's change this thing to 0.13 seconds. Okay, next stage 2, you need to make sure 4 amperes pickup current and the time is 0.38 seconds. So you can see 4 amperes secondary current and 0.38 seconds. So we are happy about that. Next we need to include the last relay, that is relay 4. You know how to do it. New devices, relay model, KCG. Next step, we need to again go to here and new devices and add the current transformers. Okay, and I assume we did it. Now I already add the devices. I will show the settings quickly. For CT4, the name is CT4 and 102 1 amps. Okay, next for the relay model, again we have a phase and earth element for the CTs, both is 100:1 amps. The next thing you need to make sure, stage 1 for relay 1 settings. Stage 1 is standard inverse 1 amps and 0.0075 seconds. So you can see 1 amps 0.075 seconds, that is 0.08. So you can change this to be 0.08. Okay, stage 2 3.07 and 0.38 seconds. Okay, 3.07 and 0.38 seconds. It's a definite one. Stage 2 for relay 4. Okay, we happy about that. Everything is right. Now after you done this configuration, setting of relays, you include the relay models and make sure settings and verify the settings as well. So we did these things. We just run the load flow and we can see the load flow is successful after you included the relay model as well. And we can also verify the protection settings. After you done, you need to verify the relay settings and the CT settings. By this icon, if you go down here, we need to select for the protection one. Select the protection one. Once you selected the protection one, you can see there is icon for output. If you click this icon, is for output for protection setting. In the output for protection setting, you can generate the report which includes instrument transformer report and overcurrent protection devices, and the devices must be all devices to be selected. When you execute, you can able to see the overcurrent settings. You see bus relay 1 2 3 4, which is on bus location 1 2 3 4 respectively, and is connected to the line branch 1 to 4 respectively. And the type of the relay we using from Alstom is our vendor, and the model of the relay we using KCGG142 1 amps relay. And for relay 1, we have two settings as we done previously. We applied stage 1 and stage 2. Stage 1 primary current is 100 amperes, stage 2 is 1015 amperes. And the time dial settings which we applied, stage 1 is 0.25 seconds with standard inverse, and stage 2 is 0.38 second definite time. The same principles will applied for relay 2, relay 3 and relay 4. So we just want to verify our settings which we applied already in the relay models. If you want, you can open the relay manual quickly and you can see this is the settings, this already there, and these are the settings that we looking from that Digsilent environment, which corresponds to your relay manual to the table 2.6, the protect relay settings. So we make sure that all the settings will be correspond to table 2.6. Okay, so we are happy about that settings. And second, we also want to verify the CT settings, that is instrument transformers. In this case, you see relay 1 to 4, each relay is having two CTs, that is one for 3 phase, that is phase, and other one for the earth element, 3I0 is for earth element. And you can see all the CT ratios is 100:1 amps, and we confirm that with your relay manual, lab manual with table 2.5. You can see all the CTs from relay 1 to 4 which having a 2 CTs for phase element and earth element, and all the ratios will be 100:1 amps. So we happy about this one as well. And last exercise I told you, if you want to export these things, this data, you can go here and export as HTML or export as Excel to export these results. If you want to prepare some report and store these things, you can export this one. Okay, so now we make sure we done all the settings, and also we verified the CT setting and we verified the relay settings as well. Now we need to verify, we need to apply a fault on different location of the network and to verify the coordination and grading with the relay. Before we do that, we also want to apply a time overcurrent plot, something similar like this. To do that, just we start from the scratch. You can just say right click and you can select show, and you can show time overcurrent plot. If you want to say add time overcurrent plot, it's going to add to the existing plot, but in my case I just say add to time overcurrent plot. You can see this is only you can see for the first relay model. What is this meaning? The full load current is 95 amperes, so the relay characteristics will operating. That is, if you go to your manual again, what is the setting we getting from in the primary current? In terms of primary current, you can see from 100 to 1015 we getting an inverse characteristics from 1015 onwards. So you see 100 to 1000, this is 100 close to that, 100 to 1015, this is a 1015, we getting an inverse characteristics curve. From 1015 onwards we getting the definite characteristics. So this is for relay 1, and you can say relay 1 cubicle 1, relay 1 is available in cubicle 1 of bus 1, okay, which is shown in red color. Next, go to the grid again and select the second relay, that is this breaker. Right click and you need to show, you see time overcurrent plot, but you need to say add time overcurrent plot. Okay, it will ask you which one, because I already have this one, but the one I added is time overcurrent plot 1. Okay, we added this one, it means you getting the second relay. In the second relay, this is your inverse characteristics and this is a definite one. For the inverse characteristic for the second relay, you also make sure according to the setting, if you come back here, 100 to 576 will be an inverse characteristics, from 576 onwards will be a definite characteristics. So you see this is 100, I think probably 200, 300, 400, 500, this is 600, but before 600 you getting a 576, so this point is 576. If you want to make sure, you can also select this line, okay, and you can include the labeling as well. If you include the labeling, you can see 576 the set point, this one. And if you want to know about this one also, we can do it. You can do this one, and relay 1 you can say this is pickup current of 1000 amperes. Otherwise, in terms of, because it's 100 amperes, 1000 means 1 times of 1000 equal to 1000 amperes. This is either in secondary amperes or primary currents, it doesn't matter. Next, we need to go for third one. For third one, the third relay, you need to select and again show and add to time overcurrent plot. Okay, otherwise we get a different time overcurrent plot every time. And select this one, okay, and you're getting the third relay. And make sure what is this setting here. So you need to select here and show this third relay. What is this one? You're getting one setting is 1 amperes, I setting secondary is 1 amperes and 0.3 seconds. So if you look here in the manual, you getting 100 to 400, so it means 100 to 400 amperes. This is 400, 100, 200, 300, 400. Up to 100 to 400 you get a inverse characteristics. From 400 onwards you getting a definite characteristics. Okay, next we go for the fourth relay, that is the last relay. You can select this model, sorry, only the cubicle. Right click and then show and add to time overcurrent plot, and select the time overcurrent plot. You click it and you can come to your plot. You can see the fourth relay, but if you want to see these timings here, you can also label this one as well. Let's say it like this. So this is your fourth relay, but if you look the time, you're getting 100, 200, 300. So it means from 100 to 301 or 2, something like that. What is the data is given? 100 to 307. Okay, so 100 to 307 is somewhere here. You're getting an inverse. From 307 onwards is getting a definite one. Okay, we are happy about that now. Now we need to apply a fault on the different location of the network, and also we need to verify the grading between the relays. Before we apply the fault, we need to apply the gradings. For the gradings, you can, as in the manual is specified already, if you go down how to apply the grading of 0.3 seconds. Okay, so you need to set a grading of 0.3 seconds in the Digsilent environment. To do that, what you want to do, right click the time overcurrent plot and then edit will open the time overcurrent. Let's see this one. You see, we are exactly like that. I will show you again. Right click and go to edit. After you have edit, you can go to the options. In the options, you can see the grading margin here. In the down, you can see the grading margin. The grading is plus or minus 0.2 seconds. But in our case, according to the manual, we need to change to 0.3 seconds. You can click OK. And if you apply, this will be applied for all the relays. If you go here, if you select relay 2 and go to options, you can see the same grading. So it means the grading will apply for all the relays. Okay, again I repeat the step. Right click, edit, and then you go to the options and you can see the grading value and change the grading to be 0.3 seconds. And you can also use the current values in primary amperes, or you can use the secondary as well and show all the relays, or you want to show only the phase element or earth element or negative sequence, it depends, but I leave it as. And also the characteristics, either you show the trip characteristics or the total clear characteristics, but I leave it as it is. Okay, we happy about that. Now according to the manual what is saying, so we follow this step and we apply this 0.3 seconds according to the manual procedure. So now we need to come back to the description step. The first step saying to model the given power system network and verify the load flow results. So it means we already model the network and we verify the load flow results. So we happy with number 1. Number 2, include the current transformers and the buses 2 to 5 and verify the CT settings. So it means we already include the buses, the current transformer right side of the buses were 2 to 4. I think it's 1 to 4, and we also buses 2 to 5. No, it must be buses. Okay, this must be buses 1 to 4. Okay, and also we have the relays on buses 1 to 4. Okay, we have the buses relays on buses 1 to 4, and we also verified the settings as well. So this step also is done over current relay settings as well. The next step, verify the relay coordination and tripping time for the 3-phase unbalanced event at different location of the network as given in table 2.7. I think this one also we applied already and we verified. So this is, we applied a fault on different buses. We applied a fault on different buses and we verified the tripping time and the fault current for these locations. We happy about that. What is the next step? So we happy about our step 3 and step 4 as well. Now we need to include the time over current plot for on the buses. I think this is 1 to 4. On the buses 1 to 4, so we can also see we include the time over current plots. That is, this is a plot. This is a plot that we include for relays 1 to 4. Okay, we happy about that as well. We did this point. And next, plot the time over current plot. Plot the time over current plot for the 3-phase unbalanced fault at location buses 2 to 5 individually and verify. This one you can go buses 1 to 5. Okay, it doesn't matter because we have the faults on all the cases. And also we need to apply the 3-phase unbalanced fault of bus 5 and verify the tripping and grading between the relays R1 to R4. That we can do quickly. So we need to apply a fault here. Calculate short circuit. It is an unbalanced short circuit. Execute. And when you apply bus fault, what is happening? We expecting this relay must trip and this relay must trip and this relay, everything will trip, but there will be a coordination and the grading between the relays must apply. Go to the time over current plot to verify this criteria. So you can see from here, we see the relay, your relay 1 will tripping 0.25 seconds, your relay 2 will tripping 0.38 seconds, and relay 3 is tripping 0.13 seconds, and also your relay 4 will tripping 0.8 seconds. Okay, once you apply the fault on bus 4, what we did here, we applied a fault on bus 5. This is a fault on bus 5, and we also want to verify the tripping times on the fault current of all these relays 1 to 4. Let me go the characteristics curve quickly. If you look here, the fault is on the fourth end, that is close to your load side. So the first relay, if the fault is on, this is a first relay, which is our relay R4. R4 is the one, the relay which is close to the fault. So it means this relay will trip in 0.41 seconds, and the next relay will trip only with a time grading margin of 0.3 seconds, will trip again 0.78 seconds. And after 0.3 seconds again margin, this relay will trip 1.25, that is your relay 2, and after 0.23 seconds, and the first relay will trip at 1.57 seconds. But in this case we see the coordination of the relays, but we can't able to see the grading margin. In order to see the grading margin, you go to right click again and edit this plot and go to the options, but you see display automatically, we only see in the current value. But if you want to see the grading and the current together, you make sure you selecting the option display automatically current and grading, and then we can see the grading as well. You can see the grading between this relay. If I can zoom out quickly for you, you can see the grading between this relay, I think from first relay to second relay 0.314 seconds, and this relay between the grading is 0.3417, and the next relay is 0.314 seconds. So this one will giving the grading value, and this one will giving the timestamp of the each relays will tripping. Okay, so that is the we understanding the coordination and grading between the relays. And the last thing I want to show you something quickly here, we also want to look the relay wiring diagram. To understand the logical of this case, you can right click, edit devices, and you can go to this relay, and you can go here, okay, we don't need to come here again, repeat the step. You can right click, edit devices, and from here you can select and show graphic. You can see show graphic, it will open. You can close this one, you can open the relay wiring diagram. So you can see the current monitored. Okay, your current monitor, this is a phase element and this is for the ground element. That's why you can see CT for 3P and CT 3I0 for the ground element, and it having a 3 phases, that is your stage 1, stage 2 and stage 3. But in our case this relay combining, this is a relay logical diagram, wiring diagram, but in our case we only look stage 1 and stage 2 in the setting, we are not considering stage 3, but if necessary we can also go for stage 3. And if you apply stage 3, we also apply for the logical 2-3. That's why we didn't consider stage 3, and that's why we made out of service stage 3, as well as the logical 2/3 is also out of service in our case. So we applied only stage 1 and stage 2. So you applying these signals to the trip logical, you see your stage 1 is coming this signal 0 1 0, and stage 2 is coming to 1, and then whatever the things is coming, it going to issue the trip signal. And also you applied, if you want to apply the ground fault, we didn't do that, but if you want, we can apply the ground fault as well, and the same stories for stage 1 and stage 2. Stage 3 will not consider for the ground fault in this case, okay, because we are not applied stage 3 as well. Okay, but for detailed understanding, this is an overview, a just quick overview of this relay wiring diagram for Alstom KCG142 relay model. But if you want to further reading, I strongly advise to download the relay model. I think the relay, I can say the manual for the KCG142, Alstom KCG142 relay, you need to download the manual for this relay model and to read for the further understanding. Okay, and other thing I want to tell you also again, but I did specify these things in the first exercise, but again to repeat you or revise you the memory, you can go to the edit devices, because if you want to export this model, we make sure these relays are packed. In order to do that, you can go to this relay, okay, and then you can click here and you can see there is option called as pack. You need to pack that one, in order to export these relay settings and the frames from from this computer to, if you want to export the model with all the frames and the settings of the relays, we need to make sure this must be packed. But in my case I packed, but you guys, after you modeling, you make sure you pack this thing before you exporting this file. Okay, that's it all about. Quickly show you again. We model this network, and also we have seen the relay geological diagram, and also we happy about to see the characteristics curve, that is coordination between the relays as well as the grading between the relays. And according to the manual, we come to the conclusion now. So we discussed everything here. In the conclusion, what we say, this project provides the theoretical overview of the protection coordination for the overcurrent relay for the faults at the different location of the network. And also we emphasize the protection coordination and grading between the relays, and it is verified for the three-phase unbalanced event at different location of the network. And also we plotted the time overcurrent plot, and from the time overcurrent plot we verified the tripping time, the fault current magnitude, and grading between the relays using the time overcurrent plot as we shown this Digsilent environment. Okay, that's all about for today's lecture. But again, I strongly also recommend to, this is a memos that we brought down, so when you apply we need to show the power system single line diagram, and also you need to show the load flow results for different cases. This is a load flow result grid summary, edge results, bus voltage profile, and also the voltage profile of the bus terminal. And this is without you verifying the IDMT characteristics, you just showing the time overcurrent plot for the 4 relays, and then we also verifying, we are applying a fault on bus 5, and we need to show the tripping time and the grading of the relays and the coordination. Okay, that's it. And finally, I also strongly recommend you to refer the following references, that is Network Protection Automation Guide from Areva, and some 2 other standard textbooks, that is Use Protecting Relaying Principles by Lewis Blackburn and Stanley. And also you need to use the Digsilent Lab PowerFactory manual to understand the principles of coordination of the relays. And other thing, I also recommending my notes, that is your Electrical Protection Laboratory manual, which is used using the PowerFactory, and also the video clips which is available in the Blackboard, also ODrive in the CPUT Electrical department. And also I recommending to read a lab manuals that is used on SEL and Alstom relay models. Okay, that is for today. In the next lecture section we will discuss about the distance protection setting using SEL 421 relay. I hope you understand, but the thing is you need to read the theoretical concept of the protection coordination between the relays, and also understand the principles of grading between the relays. Then you need to play with the different tools to understand yourself to familiarize the coordination setting of the relays. Thank you.